Hello and welcome back to part 7 on this series on the Riemann zeta function. I've had a lot of fun doing these videos, and articulating my thoughts on this way has really helped kind of get the juices flowing on what I'm trying to achieve here. So with that being said, I've decided that it's time to play my hand. So I'm going to put my cards on the table, which means I have a lot to show you. So where last we left off, we had taken the Dirichlet-Eta function and we had factored it, similar to how Euler originally factored the zeta function, which is just this sum into a product of all primes. And I'll remind you that at this point, we can split our Dirichlet-Eta function up into two parts. We have the odd integers and the negative even integers. And if we add the odd integers to the negative even integers, we just get back our Dirichlet-Eta function. Similarly, if we take the difference, so this would be the even integers minus the negative even integers, we would just get back our zeta function. So these are equivalent and these are equivalent. We can also factor the zeta function in a similar manner, which is more akin to what Euler did originally, in that the odd integers minus the negative even integers is the same as saying the odd integers plus the even integers. So these are equal. And if we flip the signs, I'll put these over here because these are equivalent. If we flip the signs, we just get back our Dirichlet-Eta function. So that's some nice mathematical trickery, but there's a point to doing this, and that is that this particular relationship is of interest, so we'll clear these out for now. In my first video, I alluded to a unique relationship, and that if you have a system of equations in which x plus y equals 1 and x minus y equals negative x over y, this relationship holds true when you have this as our x and this is our y, and specifically where s equals 1/2, their critical line. So the question is, does this hold true if instead of just giving it 1/2, we give it a complex argument, like 1/2 plus bi? Well, unfortunately, no. This relationship doesn't hold, but it reveals the true relationship here. We can modify this slightly, where s equals 1/2 bi plus bi, we can instead say x minus y equals the negative complex conjugate of x over y, which is true even when s equals 1/2. So with 0 b, because any real number's complex conjugate is itself. So what I'm saying is that this difference can instead be represented as this ratio or division. This is our x, this is our y. We have the negative complex conjugate of it. Now, I'll remind you that this is equivalent to our Dirichlet-Eta function, as was this. The odd plus the negative even, or the odd minus the even, are the same. So what I'm going to do is substitute in this x and y for this x and y. Which looks something like this, which is a little horrendous considering how large it is. But to me, this is quite beautiful, because if you'll notice that these two are the same, so we can just substitute a placeholder variable in there, and we'll call that variable z. So we have the conjugate of z over 1 minus the complex conjugate of z. And many of you might recognize this as the geometric series, which has a very nice Taylor series expansion. And even more important, the magnitude of z is always less than 1. So in my research on the zeta function and the Riemann hypothesis, a common question is why is the critical line so important? What is particular about the critical line that makes it necessary in producing zeros? In fact, there's been a statement made that it seems arbitrary, that there's no real good reason. And my response to that is, it's the critical line where the real part is 1/2, where 1, this substitution is possible, and 2, where the magnitude of this substitution is always less than 1, which is very nice for representing things as a Taylor series. So the Taylor series of this would be this. So we have a sum. And if we kind of just put this all in the same sort of notation, so all as sums, we have 3 infinite sums in a relationship. This infinite sum times the zeta function equals the Dirichlet eta function. And what I'm going to do next maybe seem a little violent and sudden, but I think that it is useful to think about the zeta and the Dirichlet eta function in a different way, which is their integral representation. For the simple reason that at the end of the day, this all kind of comes back to the gamma function and the exponential function. So what I'm saying is we have this sum times this integral equals this integral. And if you want, if it's helpful, you can move this over. So the Dirichlet eta function over the zeta function is equal to this sum. And the gammas actually cancel out, so that's even nicer. We don't even have to worry about the gamma function anymore. And so I'll remind you that this relationship only holds true when the real part of s equals 1/2. So I can just be explicit about what my final formula is. It's the sum of this ratio equals the ratio of these integrals.